black holes and relativistic jets in active galaxies.
The history of astronomy is as old as humanity itself. From observing the skies, it gradually developed into what is now an indispensable tool for the scientific study of the cosmos. This video is dedicated to a fascinating phenomenon in our universe, active galaxies.
On a dark night with a clear atmosphere, the sky is covered by thousands of luminous points. Apart from a few planets and satellites in our solar system, nearly all of them are stars in our galaxy similar to our Sun, but located light years away. They are only a small sample of the 100 billion stars that populate our galaxy. The narrow band that crosses the sky, slightly brighter than its surroundings, is the Milky Way, the projection of the disk of our galaxy onto the celestial sphere. If we visually follow the Milky Way, we will come across the constellation Sagittarius. In that direction, in a dark spot hidden from our view, lies the centre of our galaxy. Continuing along the Milky Way from the northern hemisphere, we encounter Andromeda, a neighbouring galaxy located 2.5 million light-years away, which is just one of the estimated 100 billion galaxies in our observable universe.
Galaxies can be classified according to their shape. For instance, a typical spiral galaxy is Andromeda. Examples of barred spiral galaxies in which a bar can be seen crossing the center include M91 or our own galaxy, which is depicted here as it might appear to an observer from outside. There are also elliptical galaxies like M87, which will play a key role in this story, irregular galaxies like the Magellanic Clouds, which are the closest galaxies to ours and visible from the southern hemisphere, among many others.
These images of galaxies are obtained from light, or more generally, electromagnetic radiation emitted by the collection of their stars. Although all galaxies have a higher density of stars near their centre from which a large fraction of their radiation originates, there are some galaxies, like M87, that we call active, where this concentrated region at the galactic centre is just a few light-years across. The centres or nuclei of these active galaxies are the brightest objects in the universe. We now know that this brightness is due to the presence of a supermassive black hole with a mass ranging from 1 million to 1 billion times that of the Sun, which is capable of converting a significant fraction of the gravitational energy of the surrounding matter into electromagnetic radiation.
A black hole is a system so compact that the intense gravitational field it produces traps all nearby objects so that not even light can escape its surroundings. That is why it is called a black hole, a term coined by American physicist John Wheeler in 1967.
The scientists John Mitchell, an Englishman, and Pierre-Simon Laplace, a Frenchman, were the first to independently propose, at the end of the 18th century and only a few years apart, the existence of systems so compact that an object nearby would have to travel faster than the speed of light to escape their gravitational pull. More than a century later, in 1915, the German physicist Albert Einstein formulated the general theory of relativity, which predicted the existence of these systems, black holes, and described the effects of their presence on their surroundings. Later, other physicists advanced our understanding of their formation and properties.
The black hole strongly attracts matter in its vicinity, causing it to reach speeds close to the speed of light and temperatures so high that electrons are stripped from atoms. This forms an ionized gas composed of negatively charged electrons and positively charged ions, known as plasma. Collisions between particles in this high-temperature plasma result in the formation of a disk, called an accretion disk, and the emission of electromagnetic radiation. This emission explains the unusual brightness observed in these galaxies.
The peculiarity of active galaxies is not limited to the unusual brightness of their nuclei. In so-called radio galaxies, which emit electromagnetic radiation primarily at radio frequencies, most of the emission comes from two opposing plasma jets that appear to emanate from the galactic nucleus, extending millions of light-years into space.
The study of jets began in the second half of the last century with the development of radio astronomy. Just as an optical telescope like this, or the Hubble Space Telescope, builds an image from the visible light it receives from a source emitting such light, a radio telescope constructs images of sources that emit radio frequency radiation.
The observation of these jets marks a major success for early radio astronomy, even though structural details could not be observed at the time. This lack of resolution was due to the fact that even a radio telescope with a diameter of several meters has, at radio frequencies, a lower resolution than the human eye. The increase in resolution required to observe the jets in detail became possible with the development of the aperture synthesis technique. This technique allows images from multiple radio telescopes to be combined into a single image with a resolution equivalent to a telescope of diameter equal to the distance between the individual telescopes. This led to the creation of radio antenna arrays with equivalent apertures spanning tens, thousands, or even tens of thousands of kilometers, as in the case of intercontinental radio interferometry, which uses Earth's rotation to form the images. This technique achieves resolutions of tens of microarcseconds, 1,000 times greater than those of the most advanced optical telescopes.
A detailed explanation of the jets remains a formidable challenge, although our understanding of the physical mechanisms involved has significantly advanced in recent years. In this regard, numerical simulations have played a crucial role. In astrophysics, unlike in other branches of physics or in sciences like chemistry or biology, the inability to experiment directly in a lab with the objects under study turns supercomputers into virtual labs and complex simulations into virtual experiments used to test theoretical models. In the case of jets, the purely theoretical and largely qualitative models developed in the 1970s and 80s have been increasingly complemented by complex numerical simulations that aim to describe observations on both small and large scales, as well as the mechanisms behind jet formation. According to currently accepted models, the rotation of the accretion disk, or of the central black hole itself, produces an intense magnetic field in the region around the black hole. This magnetic field draws plasma from the inner parts of the disk and accelerates it, forming the jets. The electrons in the accelerated plasma follow spiral paths around magnetic field lines, emitting electromagnetic radiation at radio frequencies. This radiation, known as synchrotron radiation, is what we detect with radio telescopes and is what allows us to construct the images of these jets.
Continued experimental advances in aperture synthesis led to the launch of the Event Horizon Telescope, EHT, project in 2009, with the goal of capturing the first image of a supermassive black hole. Due to their larger angular size, a consequence of both their proximity and actual size, the black holes chosen were those in M87 and the one at the center of our galaxy, which is currently in a less active phase. Using radio interferometric techniques, the EHT combines radio data at a wavelength of 1.3 millimeters from radio telescopes across several continents to produce images with a resolution of 20 microarcseconds. On the 10th of April 2019, the EHT team announced the success of their project by unveiling the image of the surroundings of the black hole in M87, a bright, asymmetric ring about 50 microarcseconds in diameter, with a dark central region harboring the black hole itself. The comparison of this real image with a large set of numerical simulations of black holes with accretion disks have allowed us to interpret the observations within the framework of general relativity. To our best understanding, the asymmetric ring is the relativistically modified image of an accretion disk around a rotating black hole, known as a Kerr black hole, with a mass of around 6.5 billion solar masses. The jet does not appear in the image because it is transparent to radiation with a 1.3 millimeter wavelength.
The image of the region surrounding the black hole in M87 marked a milestone in the study of the mechanisms behind active galaxies, validating the theoretical models developed over the past 50 years. At the same time, this type of observation, together with the numerical experiments that accompany it, has definitively opened the door to studying black holes as just another type of astrophysical object. Now we await the surprises that this field of research has in store for us in the years to come.